All right, in this video, we're going to talk about 8.2. This will be the first of at least two, maybe three videos that cover 8.2. I'm not sure if I'm going to do a video on complex eigen eigenvalues yet, but I'm definitely going to do a video. This first video is on distinct real eigenvalues. Then I'm going to do a different video on the repeated real eigenvalues and decide later if I'm going to do a video on complex eigenvalues because you don't run into that a whole lot, but it is a direct extension of um, what you get from the three different cases that we have solved homogeneous linear differential equations earlier. So let's go ahead and homogeneous first order differential equations. So let's go ahead and start with 8.2.1, which is distinct real eigenvalues. And I'm just going to make a note here. If you've watched my linear algebra videos, the author there sets up the characteristic equation with lambda I minus A equals 0. I'm just going to put LA here for linear algebra. The determinant of lambda I minus A is equal to 0, where A is my coefficient matrix and lambda is my eigenvalues and I is my identity matrix. Well, the order of subtraction doesn't matter here, and the differential equations book is going to set this up with the order of subtraction being opposite here, with A minus lambda I is equal to 0. So we're going to use this, and that's going to help us a little bit later in the next section to follow what the book does in solving when there is a repeated solution. So just pay attention to the way that your book presents this. Either of these is correct. You're going to have slightly different instructions for repeated roots if you use the opposite order of subtraction. Don't worry about it. Just follow the instructions that are in your book if it doesn't follow exactly with what I'm doing here. So number one from 8.2 starts off with dx dt is equal to x plus 2y, and dy dt is equal to 4x plus 3y. And that turns into a matrix equation of x prime is equal to 1, 2, 4, 3 times capital X here. And I'm interested in this matrix equation A. Again, remember we're using this form right here. So I'm going to take the determinant of, and I'm going to list my A values out here for 3. And along the main diagonal here, where there are ones on the identity matrix, I'm going to be subtracting lambda. So that means that I have 1 minus lambda times 3 minus lambda is equal to, or I'm sorry, minus 2 times 4 is 8, and that needs to be equal to 0. So let's go ahead and negative lambda minus times a negative lambda is a positive lambda squared. A negative lambda and a negative 3 lambda is a negative 4 lambda, and 1 times 3 is 3, and 3 minus 8 is negative 5. Go ahead and do as many steps as you need there. Do it in the order that's here and rearrange it in descending order of exponents if needed. But I'm trying to get you to the point where even if we write the lambda second, we really want to have them written first like this so that we can factor into lambda minus 5, and lambda plus 1 equals 0. That gives me a lambda 1 of 5 and a lambda 2 of -1. And that tells me that using this right here, I'm not going to use the determinant now. I'm going to write that as a matrix that's augmented with the 0 matrix. So I want 1 minus 5, and then 2, and then 4, and then 3 minus 5. Augment this 0, 0. So that's -4, 2, 0, 4, -2, 0. You should always get it where this is the second row is dependent, that this is a dependent system. You're going to end up with a row of zeros always, all the time. So when I RREF this, at least one row of zeros you'll end up with. You're going to get that this changes into, and I told you I wasn't going to use brackets, and I used brackets anyways because I'm used to them. So please forgive me if that's confusing you, but I'm doing my best to remember to use parentheses for my systems here. It doesn't make a difference. Just go with whatever your teacher tells you to use. And hopefully your teacher will understand whichever notation you use. So that tells me that that K2 here, K2 is equal to 2K1, where this is my K1 column, this is my K2 column. And so this is 2K1 minus K2 is equal to 0. So I bring K2 to the other side. K2 is 2K1, and K1 is my free variable t in this case. I'm going to make that 2t. So this capital K spans 1, 2, like that is what I'm interested in, is what it spans. And that's my K1, because I'm going to be putting the C1 outside of this. That's going to take care of the T that's there. So don't worry about that T that's multiplied outside. The C1 is going to take the place of that when we talk about constant multiples of this. And for my lambda 2, we're going to have 1 minus a -1 is 1 plus 1. Then we have 2, then we have 0, then we have 4, and then we have 3 plus 1. So we have 0, and we have 2, 2, 4, 4, 0, 0, which simplifies down into 1, 1, 0, 0, like this. So x1, K1 is equal to a negative K2. So we have K1 is equal to a negative K2. And I'll let K2 be T here. So this is a negative T. When I pull the T out, that gives me a K2 of -1, 1. And that gives me an X, since this is homogeneous, I don't need to put a sub C here, but this is going to be C1 times K1 times e to the lambda 1 t plus C2 times K2 times e to the lambda 2 t. And there's my solution to my first problem there. Again, it's a pretty basic extension of what we've already been doing. You just need to have a little bit of linear algebra here to be able to find the eigenvalues and eigenvectors, and to be able to write your system of equations solution here. So let's go ahead and let's look at number 3. Number 3 starts off as dx dt is equal to 2x plus 2y, and dy dt is equal to, sorry, that's number 2, negative 4x plus 2y, and then negative 5 halves x plus 2y. Let's verify negative 4x plus 2y, negative 5 half x plus 2y. So that changes to a system of x prime equals negative 4, 2, negative 5 halves 2, and then capital X, like that. So to set up my characteristic equation, I'm going to have negative 4 minus lambda, 2, negative 5 halves, 2 minus lambda is equal to negative 4 minus lambda times 2 minus lambda minus a negative 5 is going to be plus 5, and that equals to 0. So this is going to be lambda squared plus 4 minus 2 is plus 2, and then minus 8 plus 5 is minus 3 is 0, making this lambda plus 3 and lambda minus 1, giving me a lambda 1 of negative 3 and a lambda 2 of positive 1. So I'm not going to write it in to subtract. I'm just going to do the subtraction in my head this time. Negative 4 minus a negative 3 is negative 4 plus 3. That's a negative 1. And then there's the 2 and the negative 5 halves. And the 2 minus a negative 3 is 2 plus 3 is 5. Augment that there. We know that this is a constant multiple, and that changes to zeros. And I'm going to multiply the top row by negative 1, just because that's simpler for me. So that tells me that K1 is equal to 2K2. So K1 is equal to 2K2, which I'll call 2T. K2 is equal to T. So that gives me capital K1 of 2, 1. That's my first eigenvector that goes with my first eigenvalue. Notice the subscripts match each other. This eigenvector goes with that eigenvalue. Now I'm going to find the eigenvector that goes with this eigenvalue, and that's going to be negative 4 minus 1 is negative 5, 2, negative 5 halves, 1. Again, I know that that bottom row is just going to be 1/2 of the top row. It's a constant multiple. It turns into a row of zeros. I'm going to simplify here, 5, negative 2, 0. So that tells me that 5K1 is equal to 2K2. So K1 is equal to 2/5 K2. I don't want to leave fractions in my eigenvector, so I'm going to choose a t value here that's to my benefit. Choosing t to be 5, I come up with an eigenvector of, for K2, for the span of this to be 2 and 5. And so that tells me that my solution is going to be C1, 2, 1, e to the negative 3t plus C2, 2, 5, e to the t. Let's go ahead and look at number 5. Number 5 says x prime is equal to 10, negative 5, 8, negative 12, x. So they were nice enough to write it in matrix form for me to start off with. So let's go ahead and go for my characteristic equation here. This is going to be 10 minus lambda, negative 12 minus lambda, plus 40, and that needs to be equal to 0. So this is going to be lambda squared. Then we have negative 10 and positive 12 is a positive 2. And I have minus 120 plus 40 is a negative 80. Factors of 80 that have a difference of 2 are 8 and 10. The 10 needs to be positive. So lambda plus 10, lambda minus 8 equals 0. So lambda 1 equals negative 10. Lambda 2 equals positive 8. Sticking them in up here, it's going to get 10 minus a negative 10 is 20, and a negative 5, and then 8, and then negative 12 minus a negative 10 is negative 12 plus 10 is a negative 2. I know that doesn't look like they're constant multiples of each other, but if you multiply the top row by 2/5, you get the bottom row. So this is the same thing as, again, I'm writing brackets where I want parentheses. Forgive me. So this is 4, negative 1. 0 is what that row reduces to when I divide by the common factor of 5. And this is just a constant multiple of that, like so. So K2 is equal to 4K1, making this 4T. 1K1 is T, making capital K1 equal to 1, 4. 1 lambda 2 is 8. 10 minus 8 is 2. And then this is negative 5. And then this is 8. And this is negative 12 minus 8 is negative 20. That's probably a little easier to see. The bottom row is 4 times the top row. I don't need to do any simplification in the top row. The bottom row is a row of zeros. So 2K1 equals 5K2, making K1 equal to 5 halves K2. And we start off with that being, this is K2 is T. So this is T times 5 halves and 1. Well, I want to choose T to be 2 so that K2 comes out to be 5 and 2. And that means that X is equal to C1 K1 e to the lambda 1 T plus C2 K2 e to the lambda 2 t. All right, that's it for this video on distinct real eigenvalues. I'll come back next time and do some problems from 8.2.2, which is repeated real eigenvalues. And that's a little bit more of a process with that. So we'll do that separately. But that's the basic idea. You see how that's linked with what we did with homogeneous differential equations before and the three cases that were there, and how this is just like case one. So we've talked about case one in this video. We're going to talk about what was case two in the next video. And then I might do a video on case three here. And then we'll go into some videos in 8.3, which are non-homogeneous, and they'll have the same three cases. Again, I'll definitely do case one and case two in that video, and I might do case three in that video. So watch out for those videos coming up. The next one being 8.2.2, which is case two, where we're going to have repeated real eigenvalues. See you for the next video.